Alright guys, we're going to take a look at what are called reaction mechanisms. So make sure you have this packet out that I gave you with the notes page so you can follow along and fill them out as we go. So it says reactions are often more complex than they appear because they can happen in multiple small steps called elementary steps. Together the steps make up the reaction mechanism. So all the steps combined make up the mechanism. A reaction mechanism is a proposed method by which a reaction takes place. We say it is proposed because we cannot actually prove the mechanism to be true. But to have a valid mechanism, it must satisfy each of the following rules. So we're trying to get both of these rules satisfied. So number one, the mechanism's elementary steps must add up to the overall balanced equation for the reaction. So we're going to take multiple steps, multiple kind of smaller reactions, and we want them to add together to an overall reaction. And then number two, the mechanism must agree with the experimentally determined rate law. So the rate laws that we've looked at before, where it takes the form rate equals K times our concentration to the powers. So our mechanism has to agree with whatever the rate law is that was determined through experiments, like we did in the beginning of the unit where we determined M and N and the rate constant, all of those things. So the two have to agree with each other. So what do each of these rules really mean? How do we apply them? So we're going to take a deeper look at each rule using this example. So we're going to use this reaction as our example reaction. So NO2 plus CO, carbon monoxide, makes NO plus CO2, carbon dioxide. So for this reaction, the rate law was determined to be rate equals K times NO squared. So we have our experimentally determined rate law. We have an overall reaction. So we want to see which one of our proposed mechanisms that we have down here, one or two, will satisfy both of our rules up here. So, sliding down a bit, says to determine if they follow the rules, we first add the two reactions together. So we're going to be adding these reactions together with each other. It says if a chemical produced in one step and then used in the next step, and then is used in the next step, it appears on both sides of the reaction. It can be crossed out as an intermediate. Sorry for the bells. So, alright, so an intermediate is a chemical that is made in the first step of reaction and then used in the second step. So I'm going to give you an example in this first proposal. One of the chemicals that's made here is NO3. So we're taking these chemicals, reacting them together, and making NO3. Then in the second step of the reaction, so we can call this step 1 and step 2, the NO3 is used up in the process to make the final products. So this chemical, since it's made in the first reaction and then used in the second one, is our intermediate. So we can cross out any intermediates in this reaction. So we're going to go ahead and get rid of that chemical. And then the other thing that we can also cross out are catalysts. So I'm going to add a little note here, catalyst. To recognize a catalyst, it is a reactant in the first step of the reaction and a product of the final step of the reaction. So for instance, a catalyst would be this chemical NO2 because we start with it and then we end with it in the reaction. So just one of them would be considered a catalyst. And the reason why it's a catalyst is because we've got to have at least one of them to bump into the other chemicals so that we can actually produce, we can get a collision to then produce the products. So we can go ahead and cross out one of those as our catalyst. Alright, so now that we've crossed out everything that appears on both sides, nothing else cancels, we can add them together. So we get NO2 gas plus CO gas on the left, and that forms NO gas plus CO2 gas. So this first proposal matches our reaction here when we add the reactions together. So that still is meeting our first rule that we have above. So we're going to do the same process with proposal 2. So in this one, let's see if there's any intermediates. We make CO3 and N, and then we use both the N and the CO3 in the next step. So those would both cancel with each other. Those are both intermediates. We make them in the first step, and then we form them in the second step. So there's nothing else that cancels there, so then we can bring down and add our chemicals together. And we get NO, CO2. All right, we're going to talk about this slow versus fast thing soon, so don't worry about that. So again, this one, the two reactions add to the one, our goal that we had there. So far, both of these proposals fulfill both of our rules up above, or fulfill our first rule up above, that the mechanism's elementary steps, so this would be like elementary step 1 and elementary step 2, same thing over here, add up to the overall balanced equation for the reaction. So it says, does each proposal add up to the overall reaction? Number 1, yes. Number 2, yes. So far, we are fulfilling our rules. All right, now we want to check rule number 2. We want to see if our mechanism, so if these steps, this whole thing together is called each of our mechanisms, if they agree with the rate law of the reaction. So it says, to satisfy rule number 2, the rate law of the reaction must match the stoichiometry of the slow step, or what we call the rate determining step, so of the reaction. So let's kind of break this down. The slow step, or the rate determining step, in a reaction controls the reaction. So for instance, in both of these mechanisms, the slow step comes first. That means that this first reaction is going to take some time to get through, to be producing these products, and then once they're produced, it can kind of fly through the second step and make our products. So since the first step is slow, it determines the rate of the reaction. It controls the reaction speed, because you can only go as fast as your slowest step. So it says, to satisfy rule 2, the rate law of the reaction must match the stoichiometry of the slow step. What that means is that for our slow step, the reactants that we have, their coefficients should match the exponents in our rate law. So here's an example. For instance, if the slow step of reaction was this, we'd have our two reactants. Then the rate law to match it would be rate equals K, as usual. A would be squared, because A has a coefficient of 2. And B would be to the first power, because B has a coefficient of 1. So your slow step can help you actually write your rate law. It's like a shortcut to writing the rate law and finding the orders of your chemicals. So that only works for the slow step. It says the coefficient of each of the chemicals in the rate determining step, or slow step, gives the order with respect to that chemical in the rate law, our order or our exponent. Okay. So we're going to figure that out for each of these. So we're going to write the corresponding rate law for the slow step of each of our reaction mechanisms here. So our slow step in proposal 1 is given here. So in this one, like we do with everything, we start with rate equals K, and then our chemicals. So we have NO2. We're still going to include anything that's crossed out in terms of our rate law. Okay. So NO2, there's 2 of them, so it would technically be NO2 squared, because we have 2 of them. They're just written separately to show that they're colliding with each other. And then for proposal number 2, we have rate equals K times the concentration of NO2. Its coefficient is 1, so it would be to the first power. And then CO, and again its coefficient is 1, so it would be to the first power. So we have 2 possible rate laws here. Now, in the intro to this question, it gave us the experimentally determined rate law. And our second rule is the mechanism must agree with the rate law. So this is the rate law we want, and we've figured out two different ones down here. So it says which proposed mechanism's rate determining step match the given rate law. So the ones that match this would be in proposal number 1. Okay. Which proposal's mechanism could be true? So since proposal number 1 matched and had followed both rules, then that's the one that could possibly be true for this. So these two things, these two rules kind of help us in a couple ways. They help us find an overall reaction. It can help us write the rate law for a reaction if we know which step is slow, or the rate determining step. And it allows us to kind of see if a proposed rate law matches what it should in a mechanism. So, continuing down, it says you will not need to propose reaction mechanisms in this class. So you guys don't have to come up with these like sets of reactions on your own. But you would have to determine if they're valid based on these rules. You also need to be able to write a rate law based on a given reaction mechanism, just like we did here and here. There are two different situations that may occur to write the rate law, which we're going to look at below. So situation number 1, if we want to take a reaction mechanism like the ones shown here, and we want to write their rate law, we will run into kind of two possibilities. So it says when the rate determining step or slow step is first, this is going to be our first situation. This situation is easiest to determine the rate law from. Using the reaction from the slow step, you will write the rate law using the coefficients on each reactant as the order for that chemical. So if this is our mechanism, so these two equations add up to this final one, we can determine the rate law of this final step by writing the rate law of the slow step. So our rate equals K, as always. We're going to put each of our chemicals, each of our reactants in from the slow step. So A and BC, A has a coefficient of 1, and BC has a coefficient of 1. So they're each a first order chemical, so they each raised to the first power. So this rate law would be the rate law for the overall reaction. Okay, the rate law of the slow step is the same as the rate law for the overall reaction. Alright, not too bad, hopefully. And it's all because the slow step kind of controls the reaction, so the rate's going to depend on those chemicals. Alright, again, our first step here is our slow step. So rate equals K times first chemical is NO2, coefficient of 1, so to the first power, times concentration of F2, again to the first power. So this rate law is true for the overall reaction. Okay. All right, so if we've kind of got these two situations, so if our slow step is first, we can just write the rate law of the slow step and we're good. All right, turn your page over. See what happens in situation number 2. All right, in situation 2, when the rate determining step or slow step is not the first step, we kind of get a different situation. In this situation, some intermediate chemicals, so the ones that are formed and then used, need to be replaced in our mechanism so that the rate law can be determined. All right, so it says, so we've got this reaction mechanism. They've written the rate law based on the slow step. So we've got NO to the first power and NOBr2 to the first power, given based on the chemicals in that slow step. It says, as we can see, the first step is fast while the second step is slow. If we were to write the rate law based on the second step, shown above, it would include NOBr2, and we can see that in the rate law. This is an intermediate, which is not a reactant, so therefore cannot be part of the rate law. We can't, this is kind of made in the middle of the reaction. So we don't put that chemical in, so we can't like change its concentration and mess around with it. So it can't be part of our rate law. So this chemical must be replaced in the rate law. The fast reaction shows that NOBr2 is formed from NO and Br2 combining. So we can replace that NOBr2 with each of these. So we can see that this piece here, change colors here, this piece here, NOBr2, in our fast reaction really comes from these two chemicals. So we're going to replace it with the concentration of each of those with their coefficients as their exponents. So then we can bring this down. Our rate law has K equals NO. Then we've got our another NO, and we've got our Br2. So we can put these together and make it NO squared times Br2. So this is our simplified rate law. So this rate law would be the rate law for the overall reaction that we see at the bottom there. Okay, those two go together. So when our slow step comes second, it just gives us a little bit more that we have to kind of replace the chemical with, but it's not too bad. All right, let's try a couple of these. So we can see that we've got 3 reactions here. If we were to write our rate law for the slow step, we would get rate equals K times, we've got ClO2F2, that whole chemical. And there's only one of them. Its coefficient is 1, so its exponent would be 1. Now we can see that this chemical is an intermediate. It would be canceled out to make the overall reaction. So we want to see where this chemical comes from. We can go back to the first reaction where it comes from. And it's made from these 2 separate chemicals. So we're going to replace it. We're going to replace this whole piece. You're going to replace with ClO2 and F2 as separate chemicals. So our new rate law would be rate equals K times those 2 chemicals. Okay, well, that's not too bad. And then this rate law here would correspond to our overall reaction. So we can cross out our intermediates. Got that one. We've got F, and then F is used there. So now we can add our reactions together. So we've got ClO2, and we've got 2 of them, plus F2. And then we've got ClO2F, and we have 2 of those. So this rate law would correspond to this overall reaction. Okay, now let's try one more. So our slow step here, again, is our middle step. So we're going to write our rate law based on the slow step. So rate equals K times N2O2 times H2, each to the first power because their coefficients are 1. We want to check and see if anything's an intermediate. We can see the N2O2 is an intermediate. It would get canceled out. So it comes from this part, 2NO. So we are going to replace, again, this piece here with NO squared because its coefficient is 2. Alright, so then we're going to bring everything down and write our rate law. So rate equals K. This part gets replaced. So NO squared times, and bring down our H2. So this rate law would then correspond to our overall reaction. So we can cross out our intermediates. You can see our H2, one of those can cancel. I think that's it. We don't have any catalysts in this one. So we've got 2NO plus N2O here plus H2 forms. I'm going to run out of space. Get my white out. Alright. Forms, we've got N2 plus O2 plus H2O. Alright, I think that's it. So that would be our rate law for our overall reaction there. So this one's a little bit different when our rate determining step, our slow step, is not that first step. When it's the second or third one, we have to do a little more work just to kind of replace some chemicals to determine our rate law. So your practice on this, it's on the next page there. So you're going to start out, you're going to write the rate law for each of these. We're going to assume that all of these are the slow step. Okay, so if these were the slow step, we're going to just write the rate law that would correspond with them. And then some of these other ones, we're going to be adding our reactions together to get our overall reaction. Identifying any intermediates, so what chemicals.
Esmeralda Saucedo, report to attendant.
Oh, it's after school.
Esmeralda Saucedo, report to attendant.
Identify your intermediates, and then it's going to have you write the rate laws based off of those with some instructions there. Everything else is pretty straightforward, so if you have any questions, you can always ask when we return to class.